Hello! As you can probably tell, today I'm going to be talking about viscosity and terminal velocity. These are both fluid properties, and as such we're going to be covering them together, although they're not necessarily interlinked. We'll begin with viscosity. Firstly, what is it? Where do we see it? Why do we see it? Who is it? Wait, no. Moving on. Viscosity is effectively how much a fluid resists flowing due to internal resistance. This is because it's hardly viscous at all. However, were you to try and wade your way through a swimming pool, you'd encounter a lot more resistance and you'd find it a lot more difficult. This is because water is considerably more viscous than air. We can actually describe how viscous a fluid is using its coefficient of viscosity, which is derived from a formula made by Mr. Sir Isaac Newton himself. We represent this coefficient of viscosity using the Greek letter eta, depicted here. Viscosity has a few properties of its own. Firstly, we see that it's inversely proportional to the rate of flow. This was first proven by Jean Poiseuille, in 1838. Basically, this means that the more viscous it is, the slower it flows. It's like the difference between pouring water into a cup and pouring honey. We also see that as the temperature changes, so does viscosity. However, this is entirely dependent on its state, and I don't mean the emotional kind. If it's a liquid, as you increase the temperature, its viscosity decreases. But if it's a gas, as you increase temperature, so does the viscosity. Now, with that all covered, we can go on to our main topic, terminal velocity. Now, terminal velocity is effectively just the fastest speed at which an object can move. But why does this happen? So, this is our standard force diagram for an object. As you can see, we're modelling a sphere here. That's just because that's what you're going to be dealing with mostly when you use terminal velocity at our level. As I expect you may already know, whenever we have a resultant force, there's an acceleration. But if the forces are balanced, there won't be any acceleration at all, and it will maintain its current velocity, as stated in Newton's first law. Where does terminal velocity fit into all of this? Well, the arrow on the left is the resistive force due to things like friction and viscous drag. As your speed increases, so does your drag. This means that eventually the object will reach a speed where the drag is equal to the driving force. In this case, there's no acceleration, and therefore it maintains that constant speed. This means that in order for the speed to change, the driving force would have to increase or decrease. Basically, this is terminal velocity. The most common context you'll see terminal velocity is in freefall. In this scenario, our driving force is replaced by the weight of the object. This is, as I expect you know, calculated using the equation weight equals mass times gravity. Since our force is constant, we know that for a fact that if we fall for long enough, we will eventually reach a terminal velocity. This is actually the technique that squirrels use to mean that they can fall from any height. They spread out their body and make sure the drag is as high as possible so they reach terminal velocity as quickly as possible. They can survive a fall from terminal velocity. So what if you want to model something using terminal velocity? Well, you can use what we call Stokes Law. Stokes Law is an equation that we can use to find the terminal velocity of an object. So using this equation, you simply substitute in 3 of the 4 available variables and then rearrange for the final one. Now, while this equation doesn't explicitly include terminal velocity, we can rearrange it so that it does, and substitute in certain values so that we know we're getting the terminal velocity. So we know that when we're in terminal velocity, our forces will be in equilibrium. Therefore, if we place in the driving force we want to calculate the terminal velocity for as our resistive force, then we know that all the other values, if we enter them properly, should result in a terminal velocity. However, Stokes' law does have a few limitations, 5 in fact. Firstly, the fluid must be in a state of laminar flow. This means that the surrounding fluid is flowing smoothly and in parallel layers, so no turbulent flow. Secondly, the object must be spherical. This is because we can't model every possible shape or surface area in one equation. So we use a sphere. This is because at any orientation, the surface area will be the same. If we were to use a square, for example, if you were to turn it, you can get different values for the surface area which is pointing downwards if we're using free fall as an example. Thirdly, you can only use objects with one material. Fourth, the object has to be smooth so that you don't introduce any other drag or any other forces on the object. And finally, we don't want any other simulated objects to be interacting with ours because that just complicates things beyond this simple equation. And so this next part, I'll be using a screen recording. I'll be showing you how to properly solve a terminal velocity question in an exam, and then I'll be giving you a couple of practice exam questions at the end, just for you to have a go at yourself. So, here's our first question, the one I'll be helping you through. Use Stokes Law to calculate the viscous drag on a ball bearing with a radius of 1 mm, falling at 1 mm a second through liquid chocolate while it's at 30 degrees Celsius. At 30 degrees Celsius, liquid chocolate has a viscosity of 100. So, first things first, we need to convert all of our units into the proper magnitude. So, 1 millimeter becomes 0.001 meters. 1 millimeter a second similarly becomes 0.001 meters per second. Next up, it's best to write down the actual equation we'll be using. So in this case, it's F, which is our viscous drag, equals 6 pi eta r then v. Just quickly make that more of an eta. So, let's start substituting in values. Firstly, we can leave 6 pi the same. That's always going to be the same. Now, our viscosity is 100. Now, our radius times 0.001 times our velocity. And that's 0.001 again. Put that into your calculator and write out the result. And we get a final answer of 1.88 times 10 to the minus 3. So that's how you'd solve your basic Stokes Law question. So attempt this question on your own. Pause it if you need, but I'll be giving a worked answer in 5, 4, 3, 2, 1. So the first thing we should do is draw a force diagram. We know that at terminal velocity, our weight will be equal to our drag. This is because the object is in equilibrium and therefore won't be accelerating at all. So the first thing to do is to find its weight, which is equal to its mass times gravity. Now, the mass of an object is equal to its density, which is symbolized by the Greek letter rho, times its volume. And the volume of a sphere is calculated using 4 over 3 pi r cubed. We can simplify this all down to weight equals rho times 4 over 3 pi r cubed times gravity, where r equals 2, as stated in the question. Our weight equals 2,580,580. So, we know that our drag force is equal to our weight here. Therefore, we can plug it into our equation for Stokes' Law. 6 pi eta radius velocity. Now, we've left the velocity variable blank as x because that's what we're trying to solve for. Now, to rearrange this, we simply take this block of maths and just move it over here and divide this number by this set in parentheses. So we get 580 over 6 pi times 0.000018 times 2 equals x. Put those values into your calculator and you get 380288947 meters per second. Obviously, this is an incredibly high number. That is because it's going to be an incredibly heavy object, and as such, it needs to be traveling incredibly quickly in order to not accelerate anymore. And these are the kind of speeds you would see in an object traveling in outer space. Alright, thank you very much for watching. That's all from me for now. Goodbye.